Hello class, so today's topic is on amino acids. And so as a reminder, as we talked about before, amino acids are the building blocks of proteins. And what the amino acids consist of is an amino group at the alpha position. And so when we talked about the alpha position, first you look at the carboxylate group. And from there, there is a carbon there. And right next to that carbon is considered the alpha carbon. And you'll see that listed here when you have this chain that is right next to that main functional group. You have an alpha carbon, and then you have beta and gamma, and then so on and so forth. And so that alpha carbon is actually, if you remember in the past from organic chemistry, it is actually a chiral center. And a chiral center is when you have four different groups attached to that central carbon. And so that four different groups is the carboxylate group, a hydrogen group, amino group, and then some sort of R side chain group. And so with an amino acid, they have different forms, which can be shown right here, where you have an unionized form where there is no charge. You see there's now a carboxylic acid group, and then a regular no charge amino group. But then when you do have charge that does exist on the amino acids, when you have both a positive and a negative charge on the same compound, that is what is called a zither ion. And that is what's written right here. And so amino acid can have a zither ion form when it has both a positive and a negative charge on the compound. And you typically, when it's in this state, it is at a net zero. So you have a plus and a minus, and so the overall net charge is zero. And so recall that I talked about before that amino acids can act as buffers. And so this is a demonstration using amino acid called glycine, which is depicted here. And what happens is, you in this graph right here, this point is at a pH 0. And now we're just slowly adding base to the solution. And as you add in base to the solution, what has happened to that pH is you start to see like it's not going straight up, but there is this curve that is happening. This is a buffer region because there is some resistance against the pH change. And then once it reaches outside of the buffer region, then that's where you see an exponential increase in the pH. And then eventually it goes to another buffer region where you start to see this resistance again with the pH. And then when it goes outside of it, then you see this exponential increase. And so when you see this change in pH, there's also a change in the form of the amino acids. And so know that there is not just like one amino acid molecule that's in here. It's this just the same type, but there's this multiple version of that amino acid that's in the solution. So when it is at a very, very low pH, that means that amino acid is the most protonated that it can possibly be at. And so that's why you see it where you have the carboxylic acid group and that amino acid is protonated. But as base is being added, then it's being deprotonated. And so now you see this deprotonated carboxylate group, but the amino group is still protonated. And so what is happening as you increase that base, now not only do we have this form of the amino acid, but we also have this form of amino acid happening at the same time, and you when you have this pKa1, that this is at the equilibrium point right here, where you have both the state of the most protonated, and then also where one of the states is starting to become deprotonated as well. And so when you continue to add on base, more of this carboxylic acid group is being deprotonated, where this is now the major species, and that is at this point right here, the what is called the isoelectric point. And you see a pi that is represented there when this form right here is the majority component. And then once again at this point, you have this net zero, and now you're adding more and more base. So now that the amino group that's protonated, it is now starting to get deprotonated. And so when now at this point, the pKa2, you have an equilibrium of the net zero form of the amino group, and when all of the amino acid group is as most deprotonated as much as possible. That is this point right here. And then as it gets more and more deprotonated, more and more of this form of the amino acid is the majority component of the solution. And this is more so of a graphical, another form of a graphical demonstration of having different forms of that amino acid happening simultaneously. So once again, at the very, very low pH, the majority is the protonated form of the amino acid. But as you add more and more base, you see now the presence of not only the zither ionic form is starting to become present along with the protonated. So they are both present in the solution. And when you reach the pKa1, that is at the equilibrium where both groups are presented, both the protonated version and the zither ionic form is present. And you add in more and more base, and now more of the zither ion is formed, and the protonated form is decreasing more and more. Eventually it gets to the point where the deprotonated form starts to form, and that is highlighted in green. And now you have the deprotonated form and the zither ion is both being present and at equilibrium at the pKa2. And then as you add more and more base, that zither ion form starts to decrease, and more of the deprotonated version is becoming more and more present. And so as I mentioned before in class, that we will have more and more concept of organic chemistry coming up in the biochemistry. So let's try not to forget the things that we learned in organic chemistry. And so remember, we have a chiral center, so you can have different configuration R and S. And so R is clockwise as far as the relationship of what has the highest priority within the different groups that are attached to the central chiral center. And just remember, R is clockwise, S is counterclockwise, and vice versa. With L is considered counterclockwise, and D is clockwise. So when we're dealing with amino acids, we're looking at D and L. And so with the D and L configuration of amino acids, we have an example of amino acid, alanine. And so you have this carbon center, with wedges that's pointing out of the plane. You have this amino group and the hydrogen group, and then what's pointing behind the plane with the dashes is the carboxylate group, and this carbon group, so this R group. And so, as far as the highest priority is this amino group, the next is the carboxylate group. And then as you go in clockwise, you're seeing that the hydrogen group, which is the lowest priority, is blocking us from getting to the third highest priority group, which is this R group. And so whenever you see this, that means you're no longer looking at it in a counterclockwise, and so you think about it written reverse, and so that is why it's in the L configuration. So this is all what we've seen in organic chemistry. Same thing here. You have the amino group has the highest priority, and it's going counterclockwise with the carboxylic acid, but the hydrogen group is blocking because it is out of the plane. If this was a dash, then it would continue to be counterclockwise, but this is a wedge, and so you have to think, okay, whenever the fourth group is blocking, you have to think of the reverse. So now it's going clockwise, and so that is D configuration. And so also notice with L and D, these are enantiomers. You should be familiar with that word, enantiomers. And that's when two molecules are mirror images of each other. So think of a line that is presented here. You see that they are direct reflections of each other. And so just remember one thing, figuring out where's your chiral center, whether or not it's an L or a D as far as configuration. And when you have L and D, they are enantiomers of each other. So they are mirror images of each other. And so as far as amino acid residues in proteins, most, if not all, I don't like, as you know, I don't like the word all because there's always some sort of exception to the rule. But we can say most is in the L stereoisomer form, where there is less than 1% found in the D configuration. But there are the amino acids that are out there that is very specific to certain enzymatic catalyzed reactions. And then cells are able to specify some synthesis of L isomers of amino acids because of their active sites of the enzymes. Those enzymes are very selective, so they have this stereospecific specification for certain reactions. And so that will come up more and more as we progress. I think mostly it comes in biochemistry too, as far as the different enzymatic activity that might be stereospecific, but just make sure that we just realize that those are very possible things that are happening, and some people utilize this stereospecific type of enzyme for certain sensor type of applications for certain drugs or certain types of proteins that they are trying to detect. And so remember that I mentioned that we have 20 common amino acids. They are classified by their R groups. And so what you have is the non-polar aliphatic R groups, and they basically just have carbons attached to it. They are not polar. You might see this sulfur group and like, okay, well, how come this is not polar? It's because we have a hydro carbon that is attached on both sides, and so it has an even charge, and so now it ends up distributing it so well that it becomes non-polar. But if we didn't have this hydrocarbon there present, then we have a polar type of aspect to that amino acid. So that's why this one falls in that group. Then we have the aromatic group, and this is more so self-explanatory, where we see these aromatic types of compounds that exist within the amino acids. And then we have polar uncharged R groups. And so where you see that sulfur once again, but it has that H group attached to it rather than the hydrocarbon. And so that is making it now a polar type of R group. And then typically where you have polar R group, you have some sort of electronegative atom that is attached. They're just not charged. And then you can have the charged version of the R groups, which is depicted here. Some are very obvious because you see the plus charge. You see histidine. You're looking at that, it's like, hold up, I don't really see a charged group with that. That's because in this book, it wrote it in the form of at the pH 7. But if you recall from previous lecture, when you have this ionization of histidine, it actually is, when it's in this form, it donated hydrogen to try to be this buffer. When I had the slideshows on buffers, which was the second lecture, so you can go back to that lesson if you're trying to get a reminder, and just notate that when it got to this pH 5, now you see that it is in its protonated form. So that is why they put it in this positive charge R group for the amino acid classification. And then this one, more so obvious across the board, you have the negative charge R groups within the amino acids. And then something else I just want you to start to become familiar with, that's why you're going to get these slides, start to know the different naming conventions, not only the structures, but the naming conventions of each of these 20 amino acids. They have its full name, and then they have different abbreviations. And so try to be familiar with all of the abbreviations, where you have these 3 letters abbreviation, and then you have a 1-letter abbreviation of each of these amino acids. So I'll let you go and review that on your own time, but try to start memorizing these sorts of abbreviation. And here's the last piece of the abbreviations of the 20 amino acids. And so, as you know, I don't like to see the word all. There are always some sort of exceptions, but mostly amino acids are stable to acid, base, and heat. Except for some exceptions, like I mentioned before. I never really liked the word all, because there's got to be some sort of exceptions that's to the rule. And here they kind of listed some of them. We have tryptophan, where you have oxidation to form some other molecule. You have cysteine that can go through oxidation as well. Then you have asparagine, can go to go through deamination, where a nitrogen group is released. Then you have glutamine that can go through deamination as well, where a nitrogen group is released. And then as far as when amino acids is in their zeta ion form, most amino acids are soluble. We'll have actually a lab that kind of goes through this a little bit, where you can see more so what amino acids is more soluble than the others, and they kind of list them right here using the 1-letter abbreviation, where you have these 10 that are less soluble than versus these 10 that are more soluble in water when it's in its zeta ion form. And so there's also some spectral characterization with amino acids. We can kind of utilize this to help classify different concentration of proteins, because as you know, proteins are the building block, amino acids building blocks is protein. So if these particular amino acids are part of the protein, we can kind of figure out spectral wise the concentration of protein that is in the solution. So with this graph here, you can see that phenylalanine has kind of the lowest absorbance, but tyrosine and tryptophan has a more distinct peak around 280, and the one that has the most absorption, you can see, is the tryptophan. And as you can see with this particular compound with the R group, it has the largest aromatic space. So you remember that electrons could be delocalized and move. So that delocalization can happen with both of these rings, and so that is what's making this tryptophan even more aromatic. And so something you should have remembered way back in general chemistry where we talked about Beer's law. It comes back again, and we're utilizing light to try to figure out the concentration of a certain molecule. And within this equation, as a reminder, you have the intensity of the incident light. So that is the light that is coming towards the sample, so your sample that's in the solution. And then you have the intensity of the transmitted light, and that is the light that passes through the sample. Usually in the equipment that they already has this value as your absorbance, and so you don't really have to try to figure out what's the exact intensity of the incident light and the intensity of the transmitted light. They just give you this as a whole as the absorption. And then once again, we have the molar extinction coefficient, which is actually the slope if you have the absorbance versus the concentration. So that is what the molar extinction coefficient is, that slope. And then L is usually 1. It's in centimeters, and usually when we have that path link, we keep it at 1 when we're doing this sort of analysis. And this is just extra information. I'll let you read this on your own. But you might just want to question, like, okay, I know we have 20 common amino acids, but what are those extra amino acids that are present? And these are just some examples that I just wanted to just give to you as far as this extra education of other amino acids that are out there that exist. And that concludes the lecture for amino acids.